I say they dream it, quantum information thermodynamicists live it. Let me break down that term. Thermodynamics, as we all know, is a branch of physics that was developed during the 1800s, that is, the steampunk era. It was motivated originally by practicality. People wanted to understand how efficiently engines could perform work. But people ended up thinking about questions in fundamental physics, like why does time flow in only one direction? Thermodynamics was developed to describe the cutting-edge technology of the day, the steam engine, so big systems of many particles, classical particles. Today's cutting-edge technology looks a little bit different. Now we have great control over small systems. For instance, this is a single strand of DNA. You can trap one end of it in an optical trap and use optical tweezers to stretch the strand. And then you can measure the work required to stretch the strand through a given distance. Of course, a lot of the very interesting experiments and technologies at the forefront today are quantum. For instance, this is a fridge in which superconducting qubits are cooled down, and cooling is a thermodynamic process. We're often relatedly interested in how information processing dovetails with thermodynamics. And a lot of very interesting experiments, apart from you and me, we as living beings are far from equilibrium, but a lot of interesting experiments are far from equilibrium. Suppose, for example, that you have a large controlled quantum system and you perturb it. How does that perturbation spread, especially in the context of chaos? These settings are very different from the old setting of the 1800s that we saw earlier. But thermodynamic concepts like work and efficiency are still relevant. But we need to re-envision the thermodynamics of the 1800s for the 21st century. We need a toolkit for performing that update, and quantum information theory offers such a toolkit. I expect that the concept of quantum information theory is not something that needs to be explained to IQuist, but just to ensure that we're all on the same page, let me recap. By quantum information theory, I mean the study of how we can use quantum phenomena to process information in ways that's impossible with just classical systems like most of today's computers. By process information, I mean solve computational problems, communicate information, secure information cryptographically, and perform high precision sensing. By quantum phenomena, I mean entanglement, the non-commutation of operators, the discreteness of spectra, how a measurement can disturb a quantum system, and more. Quantum information theory, in part, like thermodynamics, was motivated by practicalities, the promise of quantum computers and quantum cryptography and so on. But now we simply have this wonderful mathematical toolkit that's being used as a lens to gain a new perspective on many different fields in science. Chemistry, condensed matter, AMO physics, high energy physics, and thermodynamics. If you take the thermodynamics of the 19th century and update it with quantum information theory for the 21st century, you get this blend of old and new that I call quantum steampunk. Here's where I'd like to go in the rest of this talk. First, I'd like to convince you that it makes some sense to put together quantum information theory and thermodynamics. Then I'll give a specific toy example that shows how both work and information can be resources in both thermodynamics and information processing. Then I'll zoom in on one of the subfields of quantum thermodynamics under active development now. What happens if conserved charges that are exchanged by system and bath during thermalization fail to commute with each other? Then I'll talk about the opportunities in this field. But first, why does it make sense to use quantum information theory specifically to update thermodynamics? So about this slide, partially to amuse myself while I was making this talk, I peppered the talk with a whole bunch of steampunk art. So if steampunk is not your favorite aesthetic, I apologize, but hopefully this will keep you entertained or at least awake. A big question in information theory is, how efficiently can we process information? The answer I like to call the liver of information theory. When I was in 9th grade, my biology teacher said, if you ever don't know the answer to a question on a test of mine, write down liver. The liver perform some ridiculous number of functions in the human body. So if you don't know the answer to a biology question, and you respond liver, you have an anomalously high probability of being correct. Similarly, if someone asks you, what is the optimal efficiency with which some information processing task can be performed, and you answer a function of an entropy, you have an anomalously high probability of being correct. An entropy is a function of a probability distribution or a quantum state. It quantifies our uncertainty about the outcome of a measurement of the quantum state, or our uncertainty about which value is had by the variable that's distributed according to this probability distribution. So let's look face to face at an entropy. Let's see that an entropy does serve as the optimal efficiency with which some information processing tasks can be performed. So suppose that I have a message that I want to send. So I will pick on Eric Chitambar, who might be in the audience. I know Eric because of a mutual interest in quantum resource theories, which I saw that he recently gave you a talk about, but he knows much more about them than I do. But suppose that I want to send Eric a message. We agree in advance on the quantum letters that I might send, A or B or C and so on. Eric knows the probability that I'll send A, the probability that I'll send B, and so on. According to Eric's perspective, I'm sending this mixed state in which the possible letters are weighted by their probabilities. Suppose for mathematical convenience that I send some large number n of copies of this state, then I'm sending a tensor product. Into how few qubits, basic units of quantum information, can I squeeze the total message? We're talking about the information processing task of data compression. The answer, as most of you probably know, is given by Schumacher's theorem. So in the limits, as the number of copies of the state approaches infinity, the number of qubits I need per copy of the state equals the von Neumann entropy of the state, negative trace of rho log rho, which quantifies Eric's average over all the copies, uncertainty about which letter I'm sending. We've seen how an entropy can serve in information theory, but why is the function called entropy? The answer is told to us by Claude Shannon, founder of information theory. This is a Google Doodle of him from a few years ago. Shannon said that his friend von Neumann, the great physicist, Hungarian physicist of the 20th century, said, "You should call it entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name, so it already has a name. In the second place, and more important, no one knows what entropy really is, so in a debate, you will always have the advantage." That is why I personally am spending my life on statistical mechanics and information theory. But indeed, here is the fundamental relation of statistical mechanics, and here is the statistical mechanical entropy. In statistical mechanics, the entropy tells us about how spread out a probability density is across phase space. Suppose we have a system of many particles. We don't know exactly where they are. We don't know exactly what their momenta are. So we ascribe a probability density to them. And we quantify our uncertainty about exactly which microstate the system occupies with this entropy. So in statistical mechanics, as in information theory, we use entropy, or entropies, as the case may be, depending on the task we have at hand, to quantify uncertainties. I hope that I've convinced you that it makes some sense to link information theory to statistical mechanics, but how can we use that link to our advantage? I'm going to show that, in principle, we can use information and work both as resources in thermodynamics and information processing. I'll start with Szilard's engine. Szilard was another great Hungarian physicist of the 20th century. He showed that if you have information, you can use it to turn heat into work. Now, heat is useless energy, it's random, it's not being harnessed to do anything. Work is useful, well-ordered energy that's being used, for example, to power a car or push a rock up a hill. Suppose that we have a classical particle in a box. This will be a very oversimplified version of an ideal gas. Suppose that this particle can exchange heat with a temperature heat bath through the walls of the box. And suppose that we begin with one bit of information. We know that the particle is on the right-hand side of the box rather than the left-hand side. We can slide a partition into the box, then attach a rope to the partition and attach an Acme anvil to the rope. Then we can unfix the partition to let it slide. The particle is going to punch the partition. It's going to keep punching the partition until the partition gets to the far side of the box. Then we will have lifted the anvil, so we've performed gravitational work. We've taken heat from the heat bath specifically and turned it into work. How much work can we do? This sort of work is pressure volume work, so it equals this integral. We all know the form, the ideal gas law. We can solve for the pressure in terms of the volume and substitute into the integral. I'm integrating from v over 2 to v because the particle begins confined to half the box, but ends up able to be anywhere in the whole box. And we integrate, we evaluate the limits, and we find that the work we can perform on the particle, on the weight, is Boltzmann's constant times the bath temperature times log 2. So we perform this work, but we now have no idea where in the box the particle is. We've traded information for work. We can reverse this process and perform what's called Landauer erasure. Suppose that we have a particle whose location we don't know, and we want to reset the location to a well-known value. We say this is erasure. It's like taking some piece of scrap paper that has scribbles all over it and erasing it to a well-defined, well-known state. Suppose that we start off with the capacity to perform work. Then we can slide a partition into the box near a wall, and hook up our anvil, then push the partition to the center of the box. We will have to perform work because we're compressing a gas, but we've reset the bit. We've returned the bit to a known state. Now we've traded work for information. This story has deep implications for the relationship between thermodynamics and information processing. Suppose that we want to compute and compute and compute. Eventually, we're going to run out of scrap paper, which we'll have to erase. We've just seen that erasure costs thermodynamic work. So there is a fundamental thermodynamic cost to information processing. When I first learned this, it blew my mind because who would have thought that thermodynamics is so inextricably linked with information processing? But it turns out to be so. I've been telling you a story about a classical particle in a box, but gosh darn it, this talk is called quantum steampunk, so how can we put quantumness in? Here's one way. Suppose that the system we want to erase is not a classical particle in a box, but a qubit that is entangled with a reference, a memory. Again, we have a heat bath around, then we can, it turns out, erase the system state, return it, say, to the 0 state, while keeping the memory in its same reduced state, while extracting net positive work, which is odd. We just saw that erasure costs net positive work, so we might expect to have to pay net positive work in this case. It turns out that you can sort of burn the correlations between the system and the memory. You can use the entanglement as a sort of thermodynamic fuel. So in summary, we've seen that information can be used to turn useless heat into useful work, and information, work, and entanglement can all serve as resources in thermodynamics and information processing. That's something of a broad overview of quantum steampunk as a whole and a simple example about how it works. Now I'd like to dive into one of the active subfields of this field of quantum thermodynamics. It's the subfield of conserved charges exchanged between system and bath that don't commute with each other. These are the references that so far I've written on the topic, but I'm going to show you a bunch more over the next few minutes. By the way, this might be a good time to answer a few questions if there are any. So if anyone has questions, please feel free to speak up.
So there's nothing in the chat, but does anybody have any questions right now? Okay, why don't you keep going?
Okay, great. The motivation for this problem comes from textbook statistical mechanics. We often like to think about a small system interacting with a big bath. They exchange things. If they exchange just heats, then the small system can thermalize to a canonical ensemble. If they exchange heat and particles, the small system can thermalize to a grand canonical ensemble, and so on and so forth for many different things that can be exchanged, like volume, electric charge, and particles of different species. These things exchanged are globally conserved, so I'll call them charges. I'll denote them by Q alpha, where alpha indexes the charges. When we do quantum statistical mechanics, we represent these things exchanged by Hermitian operators assumed to commute with each other. This assumption is implicit. We basically never mention it, but I'll argue later that this assumption really is there. But we're doing quantum statistical mechanics, and non-commutation of operators is one of the hallmarks of non-classicality. So what if the charges don't commute with each other? Turns out that some of our intuitions can get thrown off. But it isn't obvious whether the small system can even thermalize. Here's one reason. These globally conserved charges don't commute with each other, so they don't share an eigenbasis. So they don't necessarily share a degenerate eigenspace. It's a degenerate eigenspace that can serve as a microcanonical subspace. Suppose that we were in the simple problem in which we had a small system and a big bath exchanging just heat and particles. Suppose we wanted to prepare the global system so that the small system would thermalize to the grand canonical ensemble. We'd prepare the global system with a well-defined particle number and a pretty well-defined energy in a microcanonical subspace. And if there are more conserved charges that commute with each other, then we'd need a degenerate eigenspace shared by all those charges. But such a subspace might not exist in our problem. So if we can't even prepare the global system in a useful state, why should we expect the small system to thermalize? Also, this global Hamiltonian conserves charges, so it has degeneracies, but the charges resolve the degeneracies in different ways. So the spectrum might have a strange degeneracy pattern, and degeneracies tend to throw wrenches in our expectations about thermalization. Also, at least one derivation of the form of the thermal state breaks down if conserved charges don't commute with each other. So we really do need to be asking, what happens if the charges don't commute? Here's where I'd like to go in the rest of this part of the talk. First, I'll talk about what information theory and quantum information theory tell us about that problem. Then I'll pivot from talking about theory to talking about how we can see this sort of thermalization or equilibration or whatever happens to this system in a real life scenario in the lab. Then I'll talk about the open questions, of which there are quite a lot. First, what does information theory tell us? The first mention that I know of this problem was in a paper by Ed James about information and theory and statistical mechanics. He wrote two papers called Information Theory and Statistical Mechanics in 1957. The second paper is the quantum paper. He was concerned with the principle of maximum entropy, which states that the thermal state or the equilibrium state is the state that maximizes the entropy subject to constraints. One constraint on every quantum state is normalization. But we might also know expectation values of, for example, the Hamiltonian and the particle number. Here is the von Neumann entropy that we saw earlier. If we maximize this von Neumann entropy subject to those constraints, then the state that achieves the maximum is the grand canonical ensemble. James said that the principle of maximum entropy works even if the observables don't commute with each other. And that's all he said, basically. Not quite all he said, but he wrote only one paragraph about the non-commuting problem. When I read it, I thought, this is so fascinating. No one ever talks about non-commutation or the opposite of, in this context of thermalization or equilibrium states, why didn't you say more? In particular, he doesn't talk about how a system could come to be in such a state, or what even such a physical system would look like that would be describable with such a state. He had some followers who also thought a little bit about this problem. This paper had some good physical intuition, but it had a mathematical roadblock. Then this problem was discovered in quantum information theory a few years ago. There were a couple of groups in different parts of the world that discovered this problem at the same time. And then there were 3 groups that focused on this problem of, can we derive the equilibrium state or thermal state from more physical approaches than James, all at the same time? Fortunately, we agreed that it does make sense, with some caveats that I'll talk about, to talk about a thermal state. We call this the non-abelian thermal state. And it has basically the form that you would expect. It's an exponential. This beta is an inverse temperature. HS is the Hamiltonian of the system of interest, just as in undergraduate statistical mechanics. This sum is over the charges. These mu's are effective chemical potentials. The q's are the conserved charges of the system of interest. And the partition function z normalizes the state. Again, there are some caveats about thinking about this that I can get to later. After that, this notion of non-commuting conserved charges started propagating against quantum information theoretic thermodynamics, which has been a lot of fun to see. Even though I love doing abstract theory, I ended up a little bit frustrated because it's very abstract. And I wanted to know, we're talking about these systems that exchange non-commuting conserved charges. Do any such systems exist? Or can we build such systems? How would we see this equilibration? What would we have to do? How would we have to engineer the system? How would we have to prepare it? How could we observe it? So that was the subject of this paper, which is intended to be a bridge for these non-commuting conserved charges in thermodynamics from quantum information theoretic thermodynamics to many body physics, atomic, molecular, and optical physics, condensed matter, and eventually high energy physics. So how might such a system look? An example that can generalize consists of a chain of qubits. The system of interest S consists of some small number, little n, maybe 2 qubits. The whole system consists of big N copies of the little system of interest. The rest of the copies act as an effective bath for the small system of interest, so that the whole thing is a closed quantum many-body system. It makes sense to think of as conserved charges components of the spin angular momentum, which I'm denoting by the Pauli operators. The global charges are the different components of the spin summed all across the lattice. What Hamiltonian should evolve the system? We need a Hamiltonian that satisfies 3 criteria. First, the Hamiltonian needs to conserve every global charge. Second, it needs to take quanta of every charge and hop them. Third, this Hamiltonian should be non-integrable because entangle integrability physics from conserved charges physics. We can construct such a Hamiltonian via physical reasoning. We all know the form of the ladder operators, the raising and lowering operators for the Z-type charge. And we know how to construct an operator that takes 1 quantum of the Z component of the angular momentum from site J plus 1 and hops it onto site J, and the opposite in superposition. We can construct raising and lowering operators for the X-type charge by taking the Z ladder operators and rotating them with the Hadamard operator. We can similarly construct an operator that takes 1 quantum of the X component of the angular momentum from site J plus 1 and hops it onto site J, and the reverse in superposition. We can do the same thing for Y. We need for our Hamiltonian to hop around the lattice charges of all of these types. So when we construct the Hamiltonian, we are going to take the operator that we constructed and sum over all of the components. We also want to sum over the sites, and the Hamiltonian has to conserve every global charge. That means that the hopping frequencies should be equal. You might recognize this sum as the Heisenberg interaction. I've never seen anyone else write the Heisenberg interaction in this way, but I personally like to think of the Heisenberg interaction as a two-body operator that hops non-commuting charges, namely spin angular momenta of all components, and hops them in between two sites while conserving every component of the total angular momentum. I said that this Hamiltonian should be non-integrable. The nearest neighbor Heisenberg model is integrable, but we can break integrability in two ways. We could either introduce a next nearest neighbor term, or we can make the lattice greater than one dimensional. I'm going to take the first option. So here is our nearest neighbor term. Here is our next nearest neighbor term. How should we prepare the global system if we want to see a small system thermalizing to at least near this non-abelian thermal state? We can take as inspiration the commuting case. Suppose that we have a small system and a big bath that exchange just heat and particles. How do we prepare the global system so that the small system thermalizes to the grand canonical ensemble, as we said before, in a microcanonical subspace with a well-defined total particle number and a pretty well-defined energy? We might draw on this inspiration to guess that we should prepare our spin chain with a well-defined value for every global charge. That doesn't work because the global charges don't commute. They might not necessarily share interesting eigenspaces. Is there a question? Something just popped up on the screen.
Yes, there is a question. The question is, why do we need to break integrability?
So you could run this experiment with an integrable system, and you could probably extract interesting information from it. The thinking here is, suppose that you use an integrable system, then things will still get hopped all around the lattice, but you might see signatures of integrability, whereas what we're really looking for are signatures of equilibration, thermalization. And it would be a little bit obnoxious to have to take our observations and tease out what results from integrability and what results from commuting charges. So we could do it just might add a few extra steps to the analysis.
Thanks. And there's a follow-up also. If the charges do not commute with each other, how can you assume that they all commute with the Hamiltonian?
We can construct such operators. And in particular, so for example, we constructed a Hamiltonian that did that. And you can rely on group theory in order to either find a way of constructing these operators. There is a generalization from the qubit problem that I need to write up at some point. So from the qubit problem and an SU2 symmetry to wider class of non-abelian symmetries, so you can construct analogous Hamiltonians. And also you can use invariant theory. So invariant theory is basically a part of group theory that tells us about operators that commute with all of the generators in a set of generators for your group. And in our case, in this example here, we're focusing on the generators that are Pauli operators, but you can focus on, or you can think about more general classes, more general groups, and use invariant theory there. So I agree that it's not obvious that there is a Hamiltonian that necessarily conserves all these global charges that don't commute with each other. I agree about that. It just turns out that there are some tools that we can use to characterize these operators. And shall I continue?
Yes, please, thank you.
Okay, great. So if these global charges don't commute with each other, then they might not share an interesting microcanonical subspace. Namely, they might not be able to have well-defined values simultaneously. We can solve this problem by generalizing the notion of the microcanonical subspace to an approximate microcanonical subspace. So that was defined in this paper, which is one of the very abstract theory papers. Here's the definition, basically, that we came up with. Consider the set of whole system states omega, in which if you measure any total charge, you have a high probability of getting an outcome close to an expected value, which I'll call S sub alpha. This expected value you could think of analogously to the total particle number in the grand canonical problem. But first, every state that has this property has most of its support in the approximate microcanonical subspace. So if you take the states and you project it onto the microcanonical subspace, then you'll find that most of the weight, an amount 1 minus epsilon for some small epsilon, is there. Second, every state in the approximate microcanonical subspace has this property, which basically just means that every total charge has a pretty well-defined value. We can visualize that property. It means that measurement statistics peak about expected values. I'm going to draw a cartoon plot. Along the x-axis, I'll show the possible outcomes of a measurement of some global charge. Along the y-axis, I'll show the probability associated with getting a particular outcome. We need a peak about this expected value S sub alpha, and the peak should not be too wide. Then, so actually this particular scaling came from the more many-body physics paper rather than the abstract paper, but basically the same deal. You can prove that an approximate microcanonical subspace exists, provided that the global system is large enough. So that's might be all very well and good, but how do you actually prepare some physical system in an approximate microcanonical subspace beyond the level of definitions? We came up with two protocols. One involves preparing a product state. For example, in our qubit system, you could prepare one state pointing along the plus x direction, then one pointing along the plus y direction, then one pointing along the plus z direction, and you can repeat this pattern. This protocol is quite feasible for ultra-cold atoms with single-site microwave addressing. Second, there is a protocol that we constructed using generalized measurements, positive operator valued measures. I could give more detail about that later if anybody's interested, but these look like they're basically implemented with weak measurements. So you take your system of interest, you couple it weakly to some detector, and then you measure the detector. So we've talked about a setup, a preparation, procedure, and an evolution. This evolution needs to happen under the Hamiltonian that we constructed. It takes quanta of all different charges and hops them around the lattice. We found that a time linear in the system size suffices, but the longer that you evolve the system, the more cleanly something close to the non-abelian thermal state pops up. Then what should we predict, especially in the language and toolkit of many-body physics? Looks like there's another question.
Sorry, I had trouble finding my mouse there. So the question is from Eric December: how weak are the POVMs, and is weak measurement necessary?
If you want, how about I defer that question to later, because it might be a little bit involved. But basically, when I showed that image earlier of a peak, its width gives us the weakness of the measurement. Shall I continue?
Oh yeah, go ahead, thanks.
Thanks. Okay, so this prediction that I'm going to lay out is inspired by, but different from, predictions that you could get from the eigenstate thermalization hypothesis, or the ETH. So the eigenstate thermalization hypothesis is a very widely used toolkit in many-body physics that tells us about why quantum systems that are chaotic and are isolated tend to thermalize internally. And if anyone's interested, I would be happy to give more background about this later. So we might predict that if you set up and prepare our system in the way that we described, then if you take some typical local observable O, you let the system evolve for a very long time, and then you look at the expectation value of O, you'll find that the expectation value is about the same as it would be in the non-abelian thermal state of the global system. This non-abelian thermal state has an inverse temperature that we define by taking the expectation value of the total Hamiltonian that our system actually has and setting it equal to the expectation value of the total Hamiltonian in the non-abelian thermal states. Then we can extract beta with quite a bit of work. The effective chemical potentials are defined analogously in terms of those expected values that we talked about earlier when defining the approximate microcanonical subspace. If the temperature is high and the chemical potentials are low, then you can solve analytically for beta and the mu's perturbatively. The forms of these expressions are not very important, so I'm not going to talk very much about them. I just wanted to show that this calculation is possible. You might be concerned. You might think, we don't actually have to say anything about non-commutation of the charges in order to get the same prediction. We can just use some toolkit that we already have, like the eigenstate thermalization hypothesis. How? This is the prediction that I wrote down. You can look at this term. It has 3 mu's, which form a 3 vector. You can take the z-axis and rotate it into the 3 vector and define that as the new z-axis. Then this exponential will contain a Hamiltonian term and just one more term. Now, this is the sigma z for a system of qubits. Via a Jordan-Wigner transformation, this sigma z is equivalent to the particle number of a fermionic system. So our non-abelian thermal states will come to look identical to the grand canonical ensemble, which we already know about and already know how to predict. So why do we need to say anything about non-commuting conserved charges? Is there really any new physics here? I argue that there is for a few reasons. First, our many-body physics toolkit, the eigenstate thermalization hypothesis, works well, in fact, has in it a non-degenerate Hamiltonian. Or if you apply this toolkit to, say, a Hamiltonian that conserves the total particle number, then this toolkit works if you're focusing on just one particle number sector. As we said before, our Hamiltonian conserves a whole bunch of different charges that don't commute with each other. It has some weird degeneracies. So we should not expect our already known many-body physics toolkit to work or to be justified. Second, this toolkit concerns systems that are prepared in microcanonical subspaces, which we don't necessarily have access to in the non-commuting problem. Third, the microscopic dynamics of these two problems are very different. In the grand canonical problem, just heat and particles hop between the system and bath. In the non-commuting problem, non-commuting charges of all different types hop around. So what's physically going on is quite different. Fourth, we could try to run an analogous argument on the grand canonical ensemble and the canonical ensemble. Here's the grand canonical ensemble. You could take the h minus mu n and package it up into an effective Hamiltonian h tilde. Then the grand canonical ensemble would look identical to the canonical ensemble. But we know that the two are actually physically different. That's one reason why we have these two different terms, grand canonical ensemble and canonical ensemble. Analogously, equilibration to near the non-abelian thermal states is different from grand canonical equilibration. So we have a setup, a preparation procedure, an evolution, and a prediction. What should we measure? We can measure these local observables O, or we might as well just perform quantum state tomography on the small system of interest, which is small, say about 2 qubits. So quantum state tomography, even though as the system size grows, costs more and more, is feasible for just a small system of interest. I'm going to show the results of some numerical simulations. Along the x-axis, I'll show the total number of qubits in the system. Along the y-axis, I'll show the relative entropy between the final state of the small system of interest and a thermal state. The relative entropy is a distance measure between two density operators. Its significance is it quantifies our ability to distinguish between two density operators in a hypothesis test. So here are the results. The most important pieces are these blue disks. Those are the distance by the relative entropy from the final state of the system of interest to the non-abelian thermal states. And those are the lowest points, so the prediction from the non-abelian thermal state is the most accurate. We also compared to the canonical state and the grand canonical states by analogy with similar comparisons in these much earlier papers about a different then new quantum equilibrium state. So the non-abelian thermal state prediction is the most accurate, and the accuracy grows with the system size as the points become lower and lower. This dashed line shows the best fit to the blue circles. That's polynomial in big N, which is the number of copies in the global system of the small system of interest. We can compare this with an abstract theory prediction. In this paper, we took the relative entropy of the state of the small system of interest to the non-abelian thermal states. We averaged that relative entropy over all copies of the small system in the global system. We upper bounded that average distance, showing that the average distance is fairly small. So these constants depend on parameters. Earlier, when we were talking about the approximate microcanonical subspace, we talked about the width of these peaks. Also, the peaks have certain heights. Also, the number of charges come into play. But the essential scaling is like n to the -1/2 in this prediction. Here it's n to the -5/2 or so, so the numerical simulations suggest to us that the theory is loose, it could be tightened, or at small system sizes, really it's dominated by transients that wash out, so that if we look at large system sizes, we'll see this scaling. The takeaways here are that this concept of a microcanonical subspace that is introduced to us in undergraduate statistical mechanics can generalize to an approximate microcanonical subspace to accommodate non-commutation of conserved quantities. Real physical systems can equilibrate to at least near the non-abelian thermal states, and we can realize this equilibration experimentally. So we now have a bridge for non-commuting charges from quantum information theoretic thermodynamics to many-body physics. There is a lot to be done here. First, this experiment can be run so that we could, for the first time, observe this particularly non-classical thermal state. We focused most on how this could be implemented with ultra-cold atoms and trapped ions, but other platforms look viable. And there's this notion that the non-commutation of conserved charges might be able to block thermalization to some extent. We showed that a small system equilibrates to at least near the non-abelian thermal state. But I mentioned earlier that there are some reasons to think that thermalization might not happen completely. So there might be a little extra distance from the thermal state due to non-commutation. That would be useful in quantum memories. We need materials that retain information about their initial conditions if we want to build quantum computers. From a perspective that's more of fundamental physics, we now know of 1, 2, 3, 4 mechanisms that can block thermalization in quantum many-body physics. Non-commuting conserved charges might provide another mechanism. Now is a sort of golden age for thermalization in quantum many-body physics. There are loads of great toolkits for addressing this subject, but these toolkits have not been generalized to accommodate non-commuting charges. I'm really interested in generalizing these toolkits and bringing non-commuting charges from quantum thermodynamics into many-body physics. Once we generalize those toolkits, then we can use them to see what happens to things like transport and storage in the context of non-commutation. More broadly, for quantum steampunk, I think that's what's ahead is really bringing quantum thermodynamics outside of itself to mingle with other subfields of physics. Quantum thermodynamics itself has quite a rich landscape. There are many different subfields of this field, but quantum thermodynamics is in a much broader setting in which lots of people are interested in thermalization, quantum, and information theory. I think that we can do a lot more to take tools from quantum thermodynamics, use them to answer questions in other fields, and integrate with other fields' toolkits so that we can solve each other's problems. Also, now is the beginning of the age of experiments in quantum thermodynamics. A lot of quantum thermodynamics has been theoretical. There have been a number of experiments. The number is growing and needs to grow more. In summary, we saw that quantum information theory can serve as a toolkit for re-envisioning thermodynamics for the 21st century. We saw that both information and work can serve as resources in both thermodynamics and information processing. We zoomed in on one subfield of quantum thermodynamics and talked about the non-commutation of conserved quantities in the process of equilibration. And we saw that there is a lot to be done. So in case you're interested and you want more reading, I can suggest this review. It came out a few years ago and this field is moving pretty quickly, so a lot has happened since then, but it is a great overview that describes a number of the subfields of quantum thermodynamics. If you want something quite different, I can point to my PhD thesis. I think what makes me happiest about the thesis is just that I was able to write quantum steampunk in an academic publication. And if you want something really, really different, there's this Scientific American article. I was grateful for the opportunity to write an article about quantum steampunk for Scientific American this spring. That's where my background comes from. The artists at Scientific American did a wonderful job of envisioning quantum steampunk. So in summary, if you take quantum information theory and use it to revitalize the thermodynamics of the 1800s, you get this blend of old and new that is quantum steampunk. So steampunk fans dream it, quantum information thermodynamicists live it. Thank you.
Thank you very much for a really nice talk. I certainly learned a lot and appreciate it. So we can open up to more questions. You're getting a lot of Zoom claps.
Thank you.
We can open up to more questions. If anybody has any, I can ask one if no one else pipes up. So back in your introduction, when you were talking about the relationship between work and information and heat in the kind of classical thermodynamic sense, you said something which I thought was really interesting, that in a quantum system, entanglement can be another resource added to that list that can be converted into other things, or at least the way I understood it, that's what you said. Could you say a little more about that? Is there kind of a more general statement you can make about the usefulness of entanglement to turn into useful work in a thermodynamic sense?
Sure. Let me first pull up the right slide, then I'll share my screen. Let's see. Okay. Here was that slide. The trick behind the trick is this. We saw earlier that if you have one bit, then we're not talking about entanglement. Just if you have one bit of information, you can extract up to an amount, kt log 2, of work. If you have 2 bits, then you can extract more work. Let's look at this qubit now. Suppose that it's maximally entangled with a memory. Then this qubit is not a pure bit. It's not even a pure qubit, so we can't extract any work from it. Same thing with this memory, which is in the same state. But together, these form a system of greater dimensionality, so 2 qubits pure state. And since we have a 2 qubit pure states, we can now extract quite a bit of work, more than we could extract from 1 pure qubit. We use part of that work to erase this system, and we still have a little bit of work left over. So what's really useful, what's essentially useful, is that we have a system of associated with a Hilbert space of large dimensionality. We can extract all the work possible, and then we can use a little bit to purify this system, or I shouldn't say purify in this context, to erase the system.
Great, that makes sense, thanks. That's really interesting. Oh, we got a question in the chat. How does quantum steampunk compare or contrast with the broad field of quantum statistical mechanics, for example, Fermi gases, Bose condensates, and Ising models?
Yeah, I actually wrote an essay about that, so let me pull it up just a moment. Okay, I will drop the link into the chat here.
Great, thank you.
So there's more detail in there. One of the keys, I think, is that quantum thermodynamics takes an operational viewpoint. Thermodynamicists originally were motivated to understand engines because they wanted to pump water out of mines. And information theory is quite similar because we think a lot about people who want to communicate with each other or hide information from someone else. The perspective of thermodynamics and the perspective of information theory are operational and agent-driven. In quantum thermodynamics, we're similarly often asking, how can we use quantum phenomena not just to process information in ways that we can't process, that are impossible with classical systems only, but how can we perform thermodynamic tasks in ways, using quantum systems in ways that are impossible with just classical systems? Because we know that quantum phenomena can enhance information processing goes hand in hand in thermodynamics, so it makes sense to ask the same question about thermodynamics.
Great, thanks. And there's one more follow-up from my earlier question from someone else. Don't you have to work to erase the entanglement, or is there still energy left over from this transaction?
So, okay, so suppose that we have the states of the qubit of interest and the memory, that whole thing is a pure state, then we can just basically load it into a Szilard engine. So we basically have pure information, we load it into a Szilard engine, so we hook it up to a heat path, and we use the information to turn heat into work.
I think, so is there a way to think about, if I have a pure entangled, 2 qubit entangled state like that, can I relate the amount of information I have that I can put into that Szilard engine in a number of bits? Can I say how many bits of information that is?
So, well, actually one thing is entanglement isn't really necessary for this to happen. It's really purity, or in a somewhat technical term in the field, non-uniformity. Like the state is very far from the uniform state or the maximally mixed distribution. But at least here, so you can take the memory and keep it in its same reduced state, but still extract net positive work. But really it's the purity that's doing the work for us.
All right. Well, seeing no more questions, unless someone pipes up before I finish this sentence, let's thank Nicole again. So I can clap. If people want to unmute and clap, go ahead. Thanks a lot for joining us. And I think you've got a schedule this afternoon, but we've got a break now.
It's been a pleasure. Thank you.
Thank you.